All right, I'm going to do two more examples on how to find the sum of infinite geometric series. The first example is going to be like a repeating decimal one that we had before, but it's going to be other than. So let's say we have 17, 17, 17. This is really bad. All right, 1, 7 is repeating. All right, 1, 7 is repeating. So if we write this out, it would be 0.17 plus 0.0017 plus 0.000017 plus 0.00000017, and so on and so forth, goes to infinity. All right. Well, this is once again is a geometric series because it's a repeating decimal. We are going to start when n equals 1. We're going to infinity. All right. We're going to have our first term, which is going to be 1.17. Our ratio now, because we're moving 2 decimal places over, that's going to not be 1/10, but actually 1/100th. All right. So we're multiplying by 1/100th each time. We're going to have n minus 1. So this is geometric. We can then go through and we know the sum. And so we're going to find the sum of this infinite geometric series. We can because the ratio, once again, all right, or I should say absolute value of the ratio, because I'm going to do a problem that we need that. My other ones I did not say absolute value, but most of them are usually positive. However, we're going to go take this limit as n goes to infinity. This one, we have 0.17. We're going to have 1 minus 1/100th going to n, or going to infinity, and 1 minus 1/100th. All right. So when we have this right here, we're going to go through and try to figure this out. All right. We're fulfilling all the criteria. So when we write this, going to infinity, we realize this is going to go to 0 again. So we have 1 minus 0. The bottom is going to turn into 99 over 100. And we have 0.17 right there. Simplifying this a little bit farther, we have 0.17. And we can multiply that by 100 over 99. Multiply this by 100, 0.17 multiplied by 100, we get, well, actually, 17 over 99. Just to verify that that works out, we can go over here and put in 17 divided by 99. Press enter. And yes, I got that. Make sure your math and your fraction, all right, is in a decimal. Man, geez Louise. All right, and there we go, decimal. Let me get the decimal representation. 0.7171717 repeating, and there we have it, and that's our answer. Cool. All right, well, we're going to do another one. All right, and in this case, we're going to go over here, and we're going to do one where I haven't done this before. Okay, and we're going to have one that has a negative ratio. 1, and we're going to do infinity again. We'll have negative 3, and then this time we'll have negative 4 over 5 to the n minus 1. We'll start something like this. Now, doing something like so, once again, we're going to do the same thing. Is this geometric? All right, yes, it's exponential. I have exponent, check. Now, is our ratio less than 1 and greater than 0? Now, what I had before was you look at negative 4/7 and say, okay, that definitely is less than 1, but you actually have to take the absolute value of this, okay, the absolute value of the ratio. Make sure that it's going to be positive. And it still works out. The reason why I bring that up is because sometimes you'll have like negative 9/5, negative 9/5 in here. All right, and we'll have like that, and I'll ask students, all right, is there a geometric graph? Forget to emphasize this right here, all right, and they'll put this in here, and they'll like, oh yeah, well, it's negative. It's less than 1. And I'm like, yeah, but the absolute value has to be less than 1. So I apologize, I didn't bring that out, but the absolute value has to be less than 1. So this one actually, the ratio, absolute value of it, is actually greater than 1 because you actually have 9/5. It is definitely greater than 1. So this one diverges. So back to the one at hand, we can see this one, well, right here, our ratio, absolute value of negative 4 is 4/5, which is definitely less than 1, greater than 0, so this one does qualify. So we're going to find this one, take the limit as n goes to infinity then. Start with our value. First term, plug in a 1, and we get negative 3. All right. We're going for a 1 minus, because we plug in this 1 into here. All right, so 1 minus 1 is 0, so just going to -3 for a value. We have, now you do use not the absolute value, but the actual ratio, so we -4/5 to the n, over 1 minus -4/5. So you do want to do this way. When we go about this, we realize, okay, n goes to infinity. This still, no matter what it is still a decreasing exponential, and it's actually going to go to 0. Okay, so it's still going to become a smaller and smaller fraction when you go to infinity. All right, it'll become smaller. So this still comes to 0. So we have 1 minus 0, which is that. This right here is going to be negative times the negative, which is a positive, so we actually have 1 plus 4/5. This is where the tricky part is. We have -3. From here, we can take these and add them together. So we'll have is -3 times 1 over. Now what we have here is going to be 9/5. And what we got then, when we simplify this right here, is going to be -15 ninths. All right, and that will be our solution. That's our sum. Okay, so went through 2 different more examples of how to use infinite series. All right, one is used with a repeating decimal, other than 0.1 or 1/10, it was a 1/100th. And this one right here, we used where we had a negative ratio, because I just want to emphasize that you have to make sure you take the absolute value when you identify it, but you keep the negative ratio in when you're doing your sums. Okay, so I hope this also helps you out in clarifying some different things. So good luck, God bless on all the rest of your math.